Okay, we have three situations here. One of mass on an incline, another couple of suspended masses, another couple of masses being pulled by some net force. Okay. First, I want to see pictures of these things. Now I'm seeing some pictures, but I'm not seeing enough pictures, and I'm not always seeing enough in the pictures. Okay, some are closer than others. Some look pretty good. Okay, and you know, hopefully pictures are big enough that you have room to label. All right. Although, if you're seeing what you need to see and getting the right results, I can either read a small picture or put my glasses on and read it. It's not a big problem. But if you're making small pictures, try making bigger ones because you never know what you're going to have to label. Now, in this one, you just start out with this picture. Start out with an incline and an x-axis and a y-axis in the appropriate directions, and everybody knows what those directions are. Nobody's confused on that. And your force, okay? And then a couple of projection lines to indicate, okay, you got two components of the force, and you know exactly what to do as soon as you have that picture. And you're not just pulling equations out of the air that might or might not apply. And you're not getting the sine and the cosine mixed up, okay? Using the sine, we should use a cosine, using the cosine, we should use a sine, so that, and it's real easy to do that, depending on how complicated the picture is. If your picture looks like this and you find that this component is smaller than this one, you probably mixed up your trig functions, okay? Very easy to do it. We'll see me do it. Okay. Okay, on this one, what's the picture supposed to look like here? I think you've seen this. Picture. This mass should look like this. Okay. And your picture for this mass it's your weight, which you can call mg if you want, but you never have to use the mass here or here. Now, if you want to find acceleration of the object in the incline, you might want to get into the mass. So it's natural to kind of want to solve for the mass, but you want to do it very carefully. Okay, so you have two pictures. And if you haven't drawn those two pictures, you're at risk of getting the wrong answer, even though it's pretty intuitive. You know, this cord has to support both of these weights. This cord only has to support this weight. If you don't draw the picture, you're not following a procedure that's going to be useful to you when you need it. Okay, maybe you'll pull that picture out. And then you want to draw a diagram similar to this. I'm not going to tell you how to do it. Just draw the thing and then use the information you have to analyze the forces on each of the objects. Okay, now I'm saying a lot of intuitive stuff, okay, without applying Newton's laws. Okay. Now the big law in each of these cases is net force is mass times acceleration. You don't just pick a force and say, okay, that one's mass times acceleration. I'll ignore all the other ones, which is not what you're thinking. It's not the way you're thinking. Okay, but you are neglecting some of the forces and some of the answers you get. Okay, there's a tendency to do that. So we got to do this in a systematic way that goes right to Newton's laws. It's got to be built on Newton's laws, not on just intuition. Because even in these simple cases, some of you being misled by intuition. Okay. Okay, so let's take this one. And so, okay, so let's say I have 5 newtons law, okay? Now this, of course, means that the mass is about 0.5 kilograms. If the acceleration of gravity is rounded to 10 meters per second squared, which is totally legitimate when we're doing something in class. And when you don't need to get the precise answer to satisfy my lab. And there are good reasons for wanting a precise answer, but as we've talked about, we don't even know what the acceleration of gravity is here. It's pretty close to 9.81 meters per second squared, but we're at different elevation, and we're 2,000 feet above sea level. That puts us a little further from the center of the Earth, meaning we have less acceleration by virtue of that. The composition of the Earth close to the surface here, we might have, for some reason, because there's all kinds of geological things going on, we might have a greater concentration of mass near the surface, which will slightly affect the acceleration of gravity, down around the 100th of a meter per second squared. Okay, so anything we do with the acceleration of gravity, unless we've accurately measured it here, we don't have the means to measure it down to the 100th of a meter per second, although per second squared, although we can get pretty close. And we do that using Audacity. Okay, probably do that in lab. Depending what else we need. Using 10 meters per second squared is no different than using 9.8 or 9.81 meters per second squared. It's not quite right. Then we have to compensate for the local conditions. Now we know that everywhere on Earth is pretty darn close to 9.81 meters per second squared. So 10's about a 2% increase. Yeah, we can compensate for that 2% at the end of a problem if we know how the acceleration affects the result. We use differentials, but won't leave that on you right now. Okay, so here we have a 5 Newton force, and the question doesn't require the mass, although if you just divide the weight by the mass or by the acceleration of gravity, you can get the mass if you really want to. There's no reason, okay, because all we do is we put this now, and let's say this is at 14 degrees. We set up our X and Y axes, and everybody's setting those up correctly. That's good. So if you think to draw the picture, start with the picture. Always start with the picture. Okay. So here we have this, and here we have the weight. Okay, this is a 5 Newton force. Well, let's get rid of the details of the picture and just put our 5 Newton force there. And our 11 degrees, our 14 degrees. Okay. And the other thing we want, probably before we label anything else, is a couple of projection lines, so that we now have our X and Y components, which are what we want. Then just using our trigonometry, you can make this an angle of 284 degrees, and you just then plug in the sine and cosine. Okay, or you can take the triangles. Fx is the opposite side of this, so Fx must be magnitude of the force times sine of 14 degrees. And Fy must be the magnitude of the force times the cosine. 14 degrees. Okay, the sine and cosine of 14 degrees are pretty close to, let's say, 0.25. That seems way too high. 14 it's a quarter, it's a real close to a quarter of a radian, so the sign ought to be about a quarter. Yeah, okay. Always got to check myself. That's 2.5 newtons. And this is times I. Where your I vector is in the X direction, your J vector is in the Y direction. Okay. Well, this isn't really 5 newtons times a cosine of 14 degrees because it's in the negative Y direction. Okay. So we slap on the negative. If we use 284 degrees, we wouldn't have to slap it on. It would just come right off when we punch our buttons. Okay. But either way. And that's times your J vector. Like I said, those are weight components. Now, if you did it without the I vector and the J vector, if you have the right signs on them, okay. But think in terms of the I and J vectors because it gives you a more general representation of what's going on. And you're going to need that more general representation in some problems. Okay. Oh, and my lab probably didn't ask you to do the I and J vectors. That's I recommend the I and J vectors because it's really easy to learn. Also, again, there's different advantages. Okay. It doesn't fall off. Okay, for this one, here's your diagram, right? So actually, I might as well go ahead and do it here. No, I'm going to do it. Okay, so you got your second one, which is B newtons. So let's just say this weight is 8 newtons. Okay. Then we know that we have 8 newtons acting down. That's the weight of 8 newtons means. You don't have to find the mass. Now down here, you're going to have to do math because you got acceleration involved. Right here, you just have forces. So it just gave you forces. So you didn't have to mess with mass. Okay. So you got 8 newtons acting down and you got tension. T2, and you want to put an arrow in that. Okay. What's your principle? Well, you know intuitively that if there's 8 newtons acting down and you're trying to hold it up, it's going to take 8 newtons, right? That's good. You're welcome to think that. I encourage you to think that. But why? Why does it take 8 newtons to hold the thing up? It's because its acceleration is 0. It's in equilibrium. Okay. So I'm going to write this as negative 8 newtons times J vector. You might write it as negative 8 newtons. My lab might have done that. Okay. I'm going to do this just to be totally explicit about it. So the tension 2, this vector minus this vector has to equal the 0 vector because the acceleration is 0. And I'm going to rewrite that. I'll write it 2 steps. So F net is 0. That's a solution using physics rather than what we just know. A long experience with carried stuff around, okay? Now, that helps. Because now we can look at the diagram. For the first pass. Okay, that's tension T2 acting down, tension T1 acting up, right? There's one I didn't include here. What didn't I include? What force other than T2 and T1 are acting on this way?
Stone weight. Is it stone weight?
Not that I didn't know to include the weight, but I didn't include the weight when you give me the picture. But yeah, we also have weight. Okay, so if we do a sleep picture for this mass, do this slightly abbreviated, but we have tension T2 acting on it. And another thing about tension force, I don't know how intuitive this is to you. When you stretch a rubber band, the force in this direction and the force in this direction are the same. Tension is a force that tends to pull the ends together, or the force that tends to pull 2 points together. Tension is the same everywhere through a string or a elastic object of negligible mass. Okay, if mass isn't negligible, then the tension at every point decreases, because as you move down the object, it's got less of its own mass to support. Okay, so if this had a significant mass, the tension up here would have to exceed tension down here by the weight of the rubber band or string or whatever it is. And it does, it's just that in many cases, this is light enough compared to these to be negligible. That's why I like to use rubber bands. Strings are good too. Rubber bands and hooks are really convenient. And there's a lot of physics in rubber bands. So when we get to properties of materials, forces, Young's modulus and stuff, experience with rubber bands is going to help. So anyhow, we have this. So we have T2. We also have you might not be able to read what I wrote. I'm just going to leave it with you for right small. Okay. It's -5 newtons times J, assuming this is a 5 newton. Okay. That's right, side point to it. Okay, and then we have tension T1 acting upward. I'm going to draw T1 a little longer, because intuitively T1's got to balance both of these downward vectors. It's got to be big enough to balance. That's intuitively. Physics of it is acceleration is 0. That equals this, right? Okay, well, we seem to have 2 unknowns here. What are we going to do about that? Well, what we're going to do about that is, oh, just find T2, say newtons times J. Now, here it was plus, you gotta be careful because, yeah, at this end, T2 is positive. This end, T2 is negative. So it might have been better to write T2 here as T2 times J. So we don't accidentally say, okay, this is plus 8 newtons times J. That's down here. So we write this as T2J. T2 without the arrow over T2. We solve for the magnitude of T2. And then we would say that T2 times the J vector is plus 8 newtons times T, or just 8 newtons times T. Then we're safe up here if we write T1 as instead of vector T1, T1J. Try to put our J in here. That says T1J. Let's not apologize for that. But the principle ought to be clear. If this is then T1J without an arrow over it, then T1 is just a number. Well, it's a number of units. But it's going to come out with units. And we label this as minus T2J. So then we have T1J minus 5 newtons times J minus T2J equals the 0 vector. Well, we back out of J here, and we're going to get this is 0, and the only way that a multiple of J is a 0 vector is if that multiple is 0. So we conclude that, okay, you go ahead and fix it, whatever. I guess if anybody wants a lollipop, you pick one up on the way out. Okay. You get T1 minus 5 newtons minus T2 equals 0, but we know that T2 is 8 newtons, right? So so that T1 minus 5 newtons minus 8 newtons equals 0. And then we conclude that T1 is 13 newtons. So if we thought the T1 was just 5 newtons, we find out that we were wrong. Intuitively, if you're holding this up, you're holding all that weight up. But again, intuition only takes you so far. In this case, you just think, oh yeah, well, no, you get the right answer. But you haven't followed a rigorous process. Rigorous process does the diagrams. If you really don't want to do the I and J stuff, well, okay, take your risks. It's simple if you don't, but it's really not a problem if you do. Again, the reason I thought we decided it was a good idea to do the J's here is so that you could distinguish between this force and between this T2 and this T2. If you're just really careful to get the signs right, you don't need the J's, but the J's kind of assure that you do get right. Okay, So that's a complicated way of answering a simple question, but the question gets less simple when we get down here. Okay, so down here, what do we have? We're gonna have two free body diagrams, one for this and one for this. So let's say that, okay, we have tension T1 here and T2 here. Now, I haven't written these as vectors because it's just a tension in the string, rubber band, rope, whatever's light object is attaching these and pulling on them, okay? We know the tension T1 acts in this direction on this mass. And that it acts in this direction on this. So I'm gonna come up here. We got tension T1I. And we got, say, 5 kilograms again. The acceleration is say 8 meters per second squared with different numbers. Okay. Okay, so what's our and I'm going to say it's 8 meters per second in the next direction, 8 meters per second times I. Doesn't hurt to write I on it, it's easy. So F net is mass times acceleration equals 5 kilograms multiplied by 8 meters per second squared I, which is 40 newtons in the I direction. Okay, that looks just fine. Now, what do we do when we get to this one? Okay, well, now we have tension U2, and we have D kilograms. I think I was using 13 kilograms. No, I wasn't, but let's just say that's 13 kilograms this time. Okay. Then what do I have? I have tension 2 times I. I have negative tension 1 times I. And again, the acceleration is still the same. It's 8 meters per second squared. Well, very easy now. F net equals MA. Well, I wasn't careful to write out what F net was here, but there's only one force acting on it, so it's pretty obvious that F net is T1I, but I should have done that. Should have written T1I is this. So T1 equals 40 newtons. So that now here, when I do negative T1I, I know what T1 is. And I know that's just the magnitude of the force. The force itself is T1I. But I've got T1, so now I know what this is. Again, obvious in this situation, but if you have a much more complicated situation, you really have to keep track of it. Okay, so F net is MA, and F net. So we have negative T1 I T2 I equals mass times acceleration. You track my directions using the I vector. It should all work out. So I'm not canceling the I vector. I'm just noting that I can factor the I vector out here. And I can factor the I vector out here. And the coefficient of the I vector here has to equal the coefficient of the I vector here. So these are the coefficients of it. The coefficient of the I vector here is negative T1 plus T2. Coefficient of the I vector here is 13 kilograms times 8 meters per second squared. Okay. And now we know that T1 is 40 newtons, so that negative 40 newtons plus T2 has to be 140 newtons. So T2 is 144 newtons. Now you can check that against intuition. Intuitively, you're pulling both of these weights. Okay. So you're pulling a total of, in this case, 5 kilograms and 13 kilograms, which is 18 kilograms. Okay. If you're pulling 18 kilograms with 144 newtons of force, your acceleration is 144 newtons over 8 kilograms. 18 kilograms. 18 goes into 144 8 times. So your acceleration is 8 meters per second squared. So you can test this against your intuition. And if your analysis and your intuition don't match, then something's got to give. You got to figure out which one's wrong. Often it's going to be your intuition because physics can get pretty non-intuitive. The universe is pretty non-intuitive, especially get down to quantum mechanical level. I'm not going there. Okay, a little bit second semester. But statics problems get real non-intuitive. Acceleration problems are going to get real non-intuitive, like real quick, like in your chapter 5 assignments. Okay. So let's talk a little bit about how this moves us on into chapter 5, because these are your pretty typical chapter 4 situations you've been dealing with. Raise your level of analysis to be sure how the rules, Newton's laws apply. Okay, it all comes back to Newton's laws. And let's see how Newton's laws apply. You always need to draw these diagrams. Don't just start writing down numbers. Because then you're just writing down numbers. You're doing intuition. Okay. And you're not developing the analytical skills you need for hard problems. Okay, well, let's make the problem a little harder. Let's say in this case, same process, but you're accelerating this thing upward. F, why not 8 meters per second squared? Okay. Intuitively, since these masses, if these masses are the same as these, I think I just did. If we take this one and accelerate it upward, okay, then we're going to need the 144 newtons net force to accelerate it. But now we've got the weight acting downward. Okay. So that's the intuitive aspect of it. The rigorous analysis. Rigorous analysis. got two. So I got something to write on, got plenty of. Okay,
Yeah.
let's
Just
look
get
at the
my mouth
house.
shut.
Let's see, we got
I don't know, nation.
5 kilograms here and 13 kilograms. We got this. We got this.
Very big to choose from.
And now we've got acceleration,
What was my only
8 meters per second squared.
64.30, 64.2.
Oh,
Sorry.
8 meters per second squared, find your J vector. What's our free body diagram look like? Well, we're gonna have attention, call it T1 here, and T2 here. A 13 kilogram object will then have P1J acting upward and 130 newtons times J acting downward. That 130 newtons is automatic. If we just use the 10 meter per second square, we multiply by the half. There's the force. Okay. And then after that,
ADHD.
is T1J minus 130 newtons times J. Acceleration is 8 meters per second squared. That's the J vector. Again, I'm just using the J vector. You can use positive and negative signs if you want, because everything's along the same axis. But I'm using the J vector to keep us honest. I kind of recommend it, but it's your decision. I'm not going to count it wrong if you don't. If you make a mistake where you wouldn't have made a mistake by using the J vector, I kind of pointed out, encourage you to use that J vector. Okay. It might help you, it might not, but it's rigorous. Okay, there's your acceleration, 8 meters per second squared times the J vector. Then of course, your mass times your acceleration is F net. So that
Yeah. If he doesn't like it, then I don't know what to do. I could see this.
now that we've used the J vector to keep our signs straight, we can factor it out of both sides and say, okay, the coefficients of both sides, coefficient of J equals coefficient of J. So that this, which is now 104 newtons equals T1 minus 130 newtons.
You have
With
to
the T1 equals 234 newtons. Okay. That was easy. If you have the right picture, it's easy. Then here T2. Okay, so now we've got T2. So we've got T2J here. We've got now T1J. It's acting downward. And we've also got negative 50 newtons times J. Yeah, the negative 50 newtons is just the weight. It's actually closer to negative 49. If you want to make it negative 49.5. You may. Okay. So, there we have it. We just, all right. Okay, FNet. Equals. No, we'll cut a little bit, just go back to the J out immediately, because that's the expression you're gonna end up using in the equation you solve. Okay, now we know the T2 is 234 newtons. Even though, you know. I was gonna say something. Okay. It was right. Necessary. Okay. And F node equals MA. Which equals 5 kilograms times meter per second squared times your J. So now coefficient of F net of J here has to equal coefficient of the J vector here. Because F net is equal to F net, so this is equal to this. Okay. Now it's good to write it all out as an equation to reinforce the idea, but it should be obvious. Your algebra skills are great, but this coefficient has to equal this coefficient. So now we can simplify just a little bit. Get this. Now, two unknowns. What are we going to do about that? Well, we found T1 down here. I could have substituted it immediately up here, but I kind of wanted to keep the symbol in there. Minus. Where it comes from. And now we just add these up. We got 284 newtons, 40 newtons, which is 320 newtons. Okay. So now we've taken this. Still, it's a problem that's relevant to chapter 4. Okay. Moving into a chapter 5 situation. I want to look at two things briefly. Go back to this situation. Okay, I think I have 14 degrees. I have the weight in newtons. And if it was 5 newtons here, the mass is 0.5 kilograms. Okay. I want to get the acceleration. With the knowledge that there's also some friction. Remember the pool ball situation, right? Okay. So that pool ball might be around 0.5 kilograms. Somewhere in that ballpark, not really close. And friction is, we're going to say, is 1% of the normal friction. What are we going to do now? We're going to draw the same diagram we did before. We have 50 newtons here, 14 degrees here. I think I'm using the same numbers I did before. If not, we still know how it comes about. There's our picture. I quickly then put the numbers in. I get like 12.5 newtons times I. That's our F parallel. It's Fs. It's equal to F parallel. And we have Fy equals approximately quarter around 6. Ballpark 48 newtons if I did that right. If I didn't, put it with it. Calculate, you got your calculators, okay? That's 48 newtons times J vector, okay? Now, does this picture represent all the forces acting on the ball? Okay, so tell me. Okay, so people immediately said, well, you got friction. Well, to get friction, you got to know what the normal force is. Okay. And to be completely rigorous, I'm going to put absolute value signs around the friction, absolute value sign around the normal force. Because friction and the normal force aren't even in the same direction. So the friction is not 1% of a force in some other direction. It's 1%, has 1% the magnitude. Normal force is the force between the ball and the incline. Okay. And well, your normal force is perpendicular to the incline. Probably have time to demonstrate why. And I don't want to risk life savings of that. I'm just get the problem. Okay, there's the chalk. Now, chalk has weight, it's going to bend this thing down, right? But I really said, what direction is the chalk going to move in? Not going to move vertically. Going to go that way, perpendicular to this. Okay. Now you instantly knew what that vector was, right? What velocity vector, and you can verify, and you know what the vector parallel to this is. And you can verify if their dot product is 0. It's providing you dot product perpendicular. Dot product zeros. Okay. Well, you don't know what those vectors are, but if you have them, you'd be able to do their dot product. Very simple. And 5 minutes 0, which tells you that the force being exerted by that meter stick was perpendicular. Now, nobody saw that on the screen, so let me just illustrate it on the screen. All I did was I put the chalk here. And then I bent the meter stick down a bit the way the chalk would if it was heavier. Let it go. Right there you have it on the screen. And now you can take measurements and figure out what a vector parallel to this is and what vector parallel to the path of the chalk is, and verify that the dot product of those two vectors is 0 so that they're orthogonal and perpendicular. Okay. Well, that might not be a rigorous proof. And if we knew more about materials and compression and elasticity, we could prove it. Okay, based on centuries of measurement and experience, it always works. So we're gonna find, okay, this diagram wasn't complete until we put the normal force. Because this thing depresses or compresses the incline, depending what the incline is made of. Bends it a little bit. Now, if it compresses it well, the compression force is still at perpendicular. Okay, we have normal force. And let me change colors here because labeling can be a little confusing. That's F sub norm for normal force. And then it's going to interfere with the arrow I have over my J. But now we've got force of friction. I'll label it this way. Usually it's a little lowercase f. It doesn't even have a subscript because everybody understands that's how you do friction. But since you don't have that idea in mind, there it is. Now, picture's gotten a little messy. So let's rewrite it, redraw it. And we can take everything non-essential out of here. It's important that we understand the x component is force parallel, force component of the weight parallel to the incline. Fy is (48 newtons times J). Now we have a normal force. I'm just going to write F sub n now. And a frictional force. And I'll still write it this way. Do we have equilibrium in the x direction? Not unless there's a lot of friction, but a small enough incline or a lot of rolling friction. Try to roll that Nerf ball down that ramp that we use for the or that squeeze ball right there. Down the ramp that we use for the pool ball. It's not going to move. Or if you get it rolling, it's going to stop, whichever direction you're rolling it. Stop quicker if you're going uphill than downhill, but it's going to stop because there's a lot of friction. So that ball could be in equilibrium if it's stationary. Okay. If it's moving, well, then the frictional force combined with whatever the frictional force is big enough that it's going to slow down in either direction. You can work out the details. Okay, so we don't have equilibrium in this direction. What about this direction? Do we have equilibrium in this direction? Okay, well, let's discuss that for a second, just a second, because we're almost out of time. Okay, so I got, well, it's in equilibrium because the net force is zero. How do we conclude from this situation the net force in the y direction is zero? Okay, that's the conclusion without the reason for the conclusion. Okay, and then the same person answered bingo. Well, it's not accelerated, it's got zero acceleration in that direction. It's moving along the incline, it's not even moving in this direction. So it's certainly not accelerating in the y direction. Okay, so our analysis is very simple now. Acceleration in y direction is zero. That's equilibrium. Thus, the sum of the forces in the y direction is 0. Well, that immediately tells us what the okay. Now, and then you'll probably see whatever this component of the weight is, that is your normal force. Not always. See, don't just automatically say that this is equal to this. You have to have your whole diagram. Because, for example, if I'm also pushing in this ball at some angle with the incline, then there's a y component of that push. And that factors in here, and you have to do that to solve for your normal force. And that's what I was talking about earlier when I said things can get a little more complicated. That's a more complicated situation. Kind of like, not for the same reasons, but projecting a ball onto an incline, which you saw twice. That's intentional. Wanted to reinforce that because it's an unexpected situation with some unexpected complications. Okay. So you can have unexpected complications, and as soon as you got them, you darn well better know what your principles are and have a rigorous way of analyzing it. Okay. That's one thing I want to stress today. Now, the rest of it is easy. The force of friction. Then, and if you got to leave, just walk out the back and you can look at the last 30 seconds of the video. Okay. And that's fine. 2 minutes over time. But 1 more minute, I think you can get it. So, magnitude of your frictional force is 0.01 times the magnitude of your normal force, which is 0.01 times 48 newtons, which is 0.48 newtons. And now we can say some of the X forces is what? Now, it's first of all, your 12.5. I want to write my newtons, newtons times I, and then it's minus 0.48 newtons times J equals 12.02 newtons times, it's not times J, times I. Okay. And now what's our acceleration? Okay. This. That's too much. Sounds wrong. Yeah, my numbers are wrong. This was we didn't know it, but that was a 5 kilogram mass. Okay, so now it works. Okay. That's about 2 meters per second squared. If this thing was moving up the incline, then the frictional force would be in this direction. So with this force, in the magnitude of the net force would be 12.98 newtons, not 12.05 newtons, which is why it took that pool ball longer to come down than it did to go up. And there's the analysis that explains it. And understanding that, understanding it deeply and thoroughly, pretty good at this point. So try to make sure you do understand that. Of course, there's more to do on that lab now that we've done this. Okay. I'll also have some stuff for you to do on the lab we did last week, but I'll probably get that to you about Friday.